Okay. So it is. Can you do it again? Where is he now? That guy was reading. He's not here. He didn't come back. Yeah. Okay. So it's about a manufacturing company that they're producing tractors and they're looking at defects. Yeah. So of course, in manufacturing, there will always be defects. So given that there was defect, so the problem is what are the chances that tractor will not start? Okay. What was that? Assembly line. Okay. What fraction of companies do not start when they roll off of an assembly line? What fraction of the company's tractors? Okay, so the total tractors that the total number of tractors. Okay, so what fraction of the company's tractors do not start? Okay, the total number of tractors that do not start given all the tractors that are produced. Okay, so now that means that effective tractors that does not start, what percentage is that compared to, I mean, what is that percentage of the effective tractors compared to the total tractors that are being produced, okay, as they roll off an assembly line, okay? So we are looking at the total, not with respect to a particular assembly line, but what we are given are the information with respect to the assembly line, okay?
Please share the screen, sir.
Oh, you can. Sorry, I thought. Okay, I was so uh, engrossed in talking to you because you seem to be. Your eyes are so attentive. Okay, so now, yeah, we are looking at the total fraction of the defective tractors that are going outside. I mean, out of the manufacturing company. But then we are given information based on the each assembly line. So there are three assembly lines, and we are given the percentage of the tractors that not work. I mean, the defective tractors that will not start. I mean, it will not start. That's all. But maybe not very. It's just about starting anyway. It's not a very serious problem. So we are given the chances or the probabilities or the percentage of the tractors that will not start this in their respective lines. So 6% from red line will not start, 11% from white line will not start, and 8% from blue line will not start. Okay. And 48% of company structure are made from red line. So there's a total number, I mean the total percentage of the from the red line, 31% from the blue line, and that means from the white line is how much? 979. That's around 21. Yeah. So 21% are from the white line. So now, okay, is there a table? I thought we don't have a table. I wish we can put a table. Okay, let's create a table so that it will be more useful. Okay, let's extract the information first so that we'll enjoy this one more. So let's do impress. Blank presentation. Okay, this is a problem and we'll extract the information from it. So let's just say, okay, we'll just draw. Okay, here. Okay, now we have red line. Okay, it's so difficult. Huh. Okay, let me insert a table. Insert. Is there a table? Uh, so there, here. So the table, anyway, I have to make it faster because we're running out of time. Okay, now we have red, white, and blue line. Okay, and then chances that it will not start. So six, and then six in the red, and then the white is 11, and then the blue is 8. Okay, chances that it will not start. Okay, and then the company structure percentage of produced. Okay, so we do percentage of, let's say, total production. Okay, so 48% is in the red line, and in the white line, uh, in the blue line is 31, and then what did we say here? 21, right? Okay. So now that's the table. So what fraction of the company's tractors will not start when they roll off? So we are looking at probability of a defective tractor, probability of the defect. So we say we are looking at probability of the defective tractor, maybe defective divided by the total, okay, production. Okay. So but let's see what kind of symbols that they use. Okay, that is what we want to see. Okay, so that's the table. So now let's move. So R is the event that the factor from the red company, okay, from the what they call it company, but this is a line, W and B, red line, W line, and B line, and D is the event that the factor one side is defective. Okay, so now, probability of the percentage that it is on the red line that is given already, probability that's blue line 0.31, and probability that it's from the white line, it's 0.21. It doesn't say here. So now we are saying that the defectives that is start given that it is from the red line. So D given R, okay? So given is red, 0.06. This is defective given white, defective that is from the white line is 0.11, and probability that it is uh, defective given blue line 0.08. Okay, that one we know. That is based on the table. Okay, so now what do we want to do? Probability of the defective. Yeah, probability of the defective given the total line. So this is not, you can just say probability that the tractor is defective. Okay, because that's absolute already. Okay, so now what are you trying to find? Yeah, probability that the factor is defective. Okay, so now, okay, this is a tree diagram. So now we'll go back to decision trees. Yeah, but what we are just showing here that it can be a decision tree. You can draw it as a decision tree. You can also draw it as a Bayes rule. Okay, so now probability of the red, white, and blue line. So these are the initial given. Okay, so we know this. We know that as given from the table. And now, given that it is red, what is probability that is defective? Yeah. So here, 0.06. So that means not defective is the opposite of the complement of this one. Okay. That means that 0.94% is not effective. Give 0.94% of those not defective, that is in the red line. Okay. Now here, probability of defective in the white line, 0.11, and of course, the complement of this probability that is not defective given from the white line, that's 0.88. No, 0.89. Yeah. So and so on. Yeah. So that is the tree. So now we want to know what is the probability of it being defective. Okay, the total probability. So what we want to know is that eh, this is this defectiveness and this defectiveness and this defectiveness. Okay, how do we add them together? Okay, okay. So we follow the branch. Okay, So there are three ways for tractors to be defective, made by a red company, white company, blue company. We know this, and find all the defective ones that are, and know how many are there. So we follow this part. We follow this. So this is the one that's defective. Follow this line that's defective, and follow this line that's defective. Okay? Okay. So what is that? So and we add all those probabilities. Okay? So probability, that is, how do we write it? How do we write it? So this one, probability of it being defective. But then the probability of it being defective, remember our first equation? I mean, the equation, we'll just go back. I don't want to show you the equation below, but the equation above. That event of probability being defective, like this, probability of being a red ball. So that defectiveness is based on which line they are from. So that means that we can have this kind of probability. Probability of intersection, okay, that one. Probability that it is from the red line and it is defective. Intersection, how do we say inverted U? Inverted U, union, I mean intersection, okay, intersection of probability of the red line and intersection of defective, okay, plus probability of intersection of W, intersection of defective, and plus probability of blue and intersection of being defective. Okay. Okay. Now, okay, we don't even look at the other equation. So now we know this. We know that we can write this intersection. How do you write these intersections? Okay. Then we just say that this is equal to probability that the defective given red line, and probability of red line, plus probability of defective given white times probability of white, plus probability of blue, I mean defective given blue, and probability that is finished. Okay, that's it. Without even considering the total Bayes rule, because that is what is needed. That is what they wanted. Okay, probability of it being defective. So now, okay. So these are the intersection of the events, probability of the red, and then the, I mean, red line intersection defective, white line intersection defective, and blue line intersection defective. So now we know this from the previous one. So we have this defective, red line, probability of red, and so on. Okay. Then we add them, putting them all together. That's the total probability of being defective. Okay. So now, okay, finish. Okay, so the bonus question. So what is the probability of a tractor that came from the red company given that it was defective? Okay, so now how do we play the blame game? Blame game. So this is how we play blame game. Yeah, when you go to a company and you found that it is defective, and then you compute the probability whether it's from your line or from your friend's line, yeah, or from your enemy's line. Yeah, so now you compute the probability. Then because the boss will say, oh, there's a defective tractor. Okay, you don't want to be your finger, the boss finger to be pointed at you. Yeah, so now you compute the probability that it is defective, but it is maybe you're from the red line. Yeah. So now you compute that what is probability that indeed it is from your red line. Yeah. So now the intersection of the event of being red and it is defective, that is, we are given that it is defective. So what are the intersection of those two independent events, defective and red line? That is probability divided by probability that it was defective. So this one we all computed already. And so this, of course, we know how to compute that. That is just what? One way of computing this is what? Probability of being defective. Okay. There are many ways of computing that. Okay. Where is this? Don't be afraid to say something. Okay, nobody's looking at our video. Okay, so it's only us looking at the video. So what is this? Okay, you can write probability of what? Well, this is given a D here, so your probability that it is being defective, okay, given that it is from red line, okay, and probability of being the red line, okay, is equal to probability of being defective. Okay, well, can we write it another way? Can we write this one in another form? Just this form here. Can we write it in another? Of course we can. We can write it as probability of not starting D, but R being red, given defective. Of course, we can write that as well. And then, so now the absolute probability is that probability that it is defective. Okay? There, we can also write it like that. But what is that? Well, it is this one. This one is this, and this one is just computed there. Okay? So there are two ways you can write this, but then of course these things are, this is what we are looking for. So of course we don't use this. So this is given, defective, given that it's red. We know what if it's from the red line, the defective. I mean, given that it's from red line, we know the percentage of defective from red line, and then probability of being from the production of the red line. Yeah. So now let's continue. Clear all the drawings. So we thought that it's called Bayes rule, Bayes theorem. Yeah, it is Bayes theorem. Yeah. So Bayes theorem says that suppose that there are many events, okay, many partitions B1, B2 up to Bn, which are the outcome of the experiments, and that A is another event. Okay. A is another event that is independent of all the other events B1, B2, and B3. Okay. So so for any given number of events, BK, okay, they're all possible events from B1, B2 to B3. That's effective or not effective, and then that this is from line A, for example. So all these events, okay, and given that the independent event A, okay, independent of those B events, okay, so given a probability of a B event occurring, I mean, what is the probability of the B event occurring, BK event occurring, of all the other B's, B1, B2, and to Bn events occurring, given A. So of course we know how to write this. So this is the already we know this how to do this, independent events of BK and A, and divided by the probability, total probability of the independent event A. But if A itself is dependent on B, then we have to write it down like this. Yeah. Like in the defective case, the defective is not totally independent. It is dependent on where it is coming from and which line it is coming from. So that means in this case here, you have to subdivide it in all the other possible events, all the other probabilities when A occurred. So A occurred giving a B, okay, given a different event, a B1, up to all the other events of B's. So in this case, we are only looking at the event of BK. But because A is itself independent of all the other B events. So in this case, we need to consider all the B events given the B events when A is occurring. Okay? So we will play around with whichever, but this is the basic equation of Bayes rule that we need to follow. Well, of course, the basic one, the most basic one, is the intersection of all the probabilities of A intersection of BK. Okay? Intersection of all events. Okay? And of course, BA over here. Okay. So we just want to consider Bayes formula and help us to find. Yeah. So we will help us to find B given A if A given B is already known. Okay. So now Does that make sense? Okay. So, for example, we will be looking at, for example, what this slide is saying is that we'll be looking at B. Okay, what is the probability of B given A? Okay, when these other probabilities of A given B is already known to us. Okay. Well, is everything, if everything is not known, then of course we can compute. We cannot compute. If this is not known, then we have to find a way to do it. Yeah. On how we are going to know this event, or how we are going to consider this event, so that if this is not known, then maybe the intersections are known. Then we will use the intersections instead of the conditional probabilities. Okay. So now let's go to another example. I think this is the last example. Oh, no, because we're still at 12:50. Yeah. You have 50 minutes more, right? Okay. So now this is the last example for this one. And then we can discuss other if you have other questions. Okay. So there's another example is that 1 in 1,000 people have a rare disease A. Okay. Let's skip this one so that in case we need another slide. Insert. Uh, okay. Anyway, let's just delete this because we don't need it. Okay. So if only 1 in 1,000 people have a rare disease A, okay? True positive 0.99% if they're tested, and then false positive is 0.02% when they're tested. If one randomly tested individual, if one randomly tested individual is positive, what is the probability that they have a disease? Okay, that's the question. So now you have a rare disease A. Okay, so we have a labels. A has a disease, A0 no disease, and B the positive test results. Okay, so how do we write it in the table? Okay, uh, I don't know how to write it in the table. So we let's just write it in the table. See how we can treat this one. Where's the text? Okay, so let's just write it. Maybe this is rare disease A. Okay, so we are testing at false positive. So there are, in terms of positives, so we have, of course, when you test, there'll be, okay, delete this column. Okay, so we say positive case, and this is also positive. The whole thing is positive. This is positive. Then we merge it. Sorry, I have a class later. Okay, hold on. Just leave it there by the dog. Okay, yeah. So now there's a worker. Positive, and then we have a negative case. Okay. Okay. So those are, of course, when you test, you can test positive or negative for coronavirus, for example. But sometimes you will have a case of false positive and a true positive. Okay. So this is true and sometimes false. Okay. So that means you turn positive. Of course, in this case here, then on the negative, there will be also true negative and false negative. Okay. But the dangerous part is what is the most dangerous part here? A false negative. Yeah, because you say it's negative, but then actually you are positive. Okay. So the true negative, that's fine. So we are only looking at this one. So now of all the positive cases, so you have the true positives are 0.99. That means you're tested, you'll be, and then the false positive is 0.02. Okay. So if one is randomly tested, what is the possibility that you have the disease? So you have a disease, A has the disease, so this one has the disease, and how does it look like here? A has truly the disease, and A0 no disease, and B is the positive results. So now we say A has the disease and B has no disease. So this one is the A event, and this one is negative, so that is A0 event. Okay, A0 event. Okay. So in the A0 event, there's also a positive and a negative. The true positive, I mean true negative, and the false negative. So B, we are only looking at the B. So here I wanted to column, insert column one. No, after. Okay, maybe just to complete it. Then we merge this. Okay. Okay. But this information we don't have. So we have a true and this is a false. So in the case here, this is a B plus in the table. I'm just for completeness. So this is B minus. Okay. So there must be a B plus here and then the B minus. Okay. That is the positive test result. So in this case, B minus is the negative test results. Okay. So, so yeah. So this is the table. But we don't have information on the negative. We only have information on the positive. So let's concentrate on the positive. So now, this is the tree. So probability that examine probabilities. So we examine, how come? Oh, okay. Probability, we're saying that if one, the probability that it is positive, okay, the probability that it's positive and it has a disease A, so we are given this one. Probability that it has this one, okay. So we are looking at what is given to us, okay. So false positive and then false positive. How come this is A0? So it has to be A0 here, false positive. But you turn your positive, it is not about, this is the positive test. This is not the wrong, this is a wrong table. Yeah, this is a wrong table, sorry. So what I'm saying here, what they're saying here is that it is the actually no disease, and this is actually the person has no disease, and I mean has the disease, actual person with the disease and actual person without the disease. In this case here, my A is the person that tests positive, and my A0 is the person that tests negative. Okay, this is not correct. It should be the person with the disease. Okay. Then it will change. A with disease. And A0 is without disease. Okay. So now it will change. Okay. So if you are, what is this one? The true positive. So when you have a disease and you tested positive, that's 99%. Okay. This is false positive. Where is this? This is the testing results. Do you understand? This column here is the test results. Okay, you can test, you can test positive and negative. Yeah, you can test positive and negative. Okay, so this true is actually positive. Positive. Okay, and this false is negative. Okay, and this one is positive. Your test results is positive, and your test results here is negative. Okay, now it's more understandable now. So now, if you test positive and that is true, so that means you test positive and that is true. Okay, so this is 0.99%. This one, you test positive and it's false. You test positive and it's false is here. You understand? Okay, I hope that is, I created the table wrongly. In the first case, the heading was for the testing positive, and the heading was in this case for the test results, but the test results should be here. Okay, so now let's consider the totality. The total in this case here, they divide the disease with disease and without disease. So 1 in 1,000 people has a rare disease A. So that means the probability of this one is 1 divided by 1,000. Okay, with the disease. So what is that now? This one is 999 divided by 1,000 without the disease. Okay, so now that is why this is without disease 0.999. This is 0.001. Okay, so those are all the information that is given to us. Okay, so what is the probability that they have the disease? So the question here is, if one is randomly tested, okay, so you got, what is the probability that it has the disease? How do we write it? What is the probability that person has a disease? Okay, but then you need to go positive and we have to go test results, right? So what are those test results? What is the probability that you have the disease? Or, okay, hold on, probability that it has, if what is probability that they have the disease? What does that mean? Okay, it has the disease, A has the disease, and given that they tested positive. Okay, so that means then we can just write it. Okay, probability of, again, it has the disease intersection of positive divided by probability of being positive. Okay, so what are those? Okay, so those intersections will be the numerator. Okay, I wish I can write it down here like this, divided by, I want it to be the numerator, probability of P. Okay, and then we write it equal to, wow, nice, it looks nice there. Okay, there. Okay, so here, what will it look like? So what is this? And we will write it, probability of being positive. Okay, so now what is this? Probability of being positive given that it has a disease, and probability of having a disease. Okay, and then below, okay, probability of being positive. Okay, probability of being positive. So what are those other probabilities? Being positive that it has a disease, and probability uh, of the disease, and probability of being positive that you don't have the disease, because those are all the probabilities of being positive, and probability that you don't have a disease. Finish. Okay, finish. That's it. Just substitute. Okay. So is there probability of positive given A? That's B. Positive given A, it's given. Positive given, that's 0.99. Probability that you have the disease, that's this one, 0.01. And then probability of positive given A, positive 0.99. Probability you have a disease, this one. And probability positive and you don't have a disease, you have that. And probability you don't have a disease, it's there. Go finish. You can compute. Okay. So now this is the one, and then we can A intersection B. So yeah, can you compute? What is that?
Think.
How much is this? Come on, before we finish. It's 10 minutes. Is it correct? So that means that in this case here, we just write down here on top. Probability that you are positive and you have the disease is 0.99, and probability of the disease total probability multiplied 0.001, okay, divided by divided by probability that the numerator, you just put the numerator again, times 0.001. Is it 0.001 or one more zero? 001, okay, plus the false positive, probability of the positive 0.0